Okay. All right, so I think we are just about good to go. So I'm going to get started with just a couple of announcements. Ivan, just let me know if I cut out again, okay?
Sorry, I still have not managed.
All right, so I think we are just about.
It's extremely loud.
Oh, okay.
Yeah, I'm sorry. Let's see.
Can you just put it back in this?
Oh, just one second. Just Professor, can you speak again?
Yeah, how's the volume now?
Louder. Can you speak again?
Yep. Can you hear what I'm saying okay?
Professor, so they can hear you well now, but you're kind of cutting in and out and lagging a bit. So it seems to be, it might be the internet on your end, because this is connected to the one that the maintenance guy said that was the hardwired connection. So I can't do anything more in terms of the connectivity from my end. So.
Okay, well, I guess we'll try. I don't think it's the internet on my side. Mine's hardwired and I've had no issues with it, but let's try to get rolling. So good morning, everyone. I think today we should hopefully be okay with technology. The projector has been fixed. It was broken last class. There are some connectivity issues, I think, in Marcus, and I've been told it really helps if you avoid connecting to the wireless internet in Marcus. So if you are not using your laptop to take notes or things like that, if you could put them away. If you are, that's fine, but if you are not, it will just help keep the stability of the live stream. So a couple quick announcements to get us started. So hopefully you saw in my email that this week, the two reviews, the one yesterday and the one on Thursday, are going to be on graph transformations. So that is something that we do and we may or may not have time to review. And so if that's not something you remember doing, or if it's been a while, you may want to stop by William's session on Thursday. So that's things like moving the graph up or down, left and right, and flipping it. So those are the types of things he'll be talking about, and he'll be going over the tool Desmos, so that if you want to learn how to graph on that while you're doing work, you can learn a little bit about that. So today, we are going to be covering a couple of brief chapters for review of things that you may or may not have seen recently. And so the three sections that we're going to cover today, we have 1.4, which is economics, 1.5, which is exponentials, and 1.6, which is the natural logarithm. Now, because the technology is being so spotty, I'm not sure we'll get to all of them. So we're going to do these in the order that I think makes the most sense. So we're going to talk about exponentials first, then we're going to talk about economics, and if we have time, we'll do the natural log, and if we don't, that's really easy to review, and I'll send you a video. So we're going to start by talking about 1.5 and then go back to 1.4. So we're going to talk about exponential functions first. So I'm going to go ahead and turn on my dot cam here. Okay. Now, when we talk about exponential functions, one of the main things that we run into is just identifying when we're actually working with an exponential function. And so one of the things that we don't explicitly talk about is the other type of function that looks like this, which is a polynomial. So I just want to remind you for a minute that a polynomial is going to be a function where you have something like x to the n. So for example, x squared, x cubed, x to the 10th. Functions that have these types of terms are called polynomials. And here, the variable is in the base. Okay, so that's one of the distinctions we look for when we're looking at a function to determine what kind of function it is. Now with exponential functions, these are going to be anything that's of the form y equals k times a to the x. So let's talk about what this means. So k is a constant, a constant, but here the variable is in the power. So that's what's going to make this an exponential function, is that our variable is up in the power. So some examples of exponential functions, you might have something like y equals 2 times 3 to the x. You could have something like y equals 5 to the t. These both have our variable up in the power. That's what makes them exponential. Now, one mistake that students often make is when you have a number in front and a number in the base, we try to combine them, but you can't do that. So the 3 to the x is the function part and 2 is a constant. So we can't make this 6 in any way, shape, or form. The 3 is attached to the x and cannot be changed. So just be careful about that. So the first thing we want to do is just get comfortable with exponential functions. And so the first thing I want you to do is just take a minute to practice plugging in into exponential functions. So there's 4 exponential functions here. And what I want you to do is take out your calculator and try to plug in t equals 3 into each of these functions, just so that you get comfortable with the syntax of plugging things in. So I'm going to give you 2-ish minutes. The TAs will come around. So if you're not really sure how to put it into your calculator, they can show you. But I want you to get a numerical value for each of these 4 to practice plugging into exponential functions. So go ahead and try that. All right, take about 30 more seconds to finish up whatever part you're working on. All right, So hopefully you are getting the same values that I am when you're plugging in t equals 3. If you are not, then it's worthwhile to ask a TA after class or stop by Drop-In Help just to make sure you're getting the syntax right. But I do want to talk about the last one, and I do want us to do this together. So y equals 2 times e to the t. Now, e is a number, right? And it's sort of like pi, where pi is a number, but we use a symbol to represent it because it's an important mathematical constant. And so e, when you plug this into your calculator, has a special button on your calculator. So I'm going to show you my calculator. Yours might not be in exactly the same place, but I'm hoping this will help you find it overall. So let's see. Let me move this down here for a second. So to put this in, I start with my 2 times. Now my E button is hidden back here behind the natural log. So it says ln, mine is right next to the 4, and in the blue, it says e to the x. So in order to add the e, I have to push second, and then down here, I push the button that says ln, and it puts in the e, and then I can put in whatever number I want, which here, I'm trying to evaluate it at 3. So that's where that e is hidden on your calculator. It's behind the ln, and you have to use the second. It should be somewhere in this row, even if you have a different TI calculator. If you have a Casio or a different type of graphing calculator, it'll be hidden somewhere else. And if you're using a laptop instead, usually you can just type in the E. So then when you hit enter, it's going to compute that number. So E, the mathematical constant, is an irrational number that goes on forever. It's about 2.71, but I can always remember what it is by doing E to the 1, because anything to the 1 is just itself. So that'll give you the decimal that you can look at and see what's going on there. So again, E is just a number. It often comes up with exponential functions. We'll talk about that in a few minutes, but that's how we plug things in, okay? So the reason why exponential functions become so important in this class is because in the natural sciences and the life sciences, we often talk about growth and decay. So how much is a population growing? How much is the reaction growing or decaying, right? Things like that. And so when we apply exponentials to this specific scenario of growth and decay, we often use the form P equals P naught a to the t, or P naught 1 plus r to the t. So this is the same form that we had up here, but instead of k, we're calling it P naught, and I'll talk about that in a second. And then our a, our base, which is a number, is written as 1 plus r. So let's talk about P naught. The word naught is just this little subscript of 0. When you hear someone say P naught or K naught or Q naught, right? It just means that there's this little subscript of 0. And what that means is that it's an initial amount. So typically when we're using this form, we're talking about populations. And so this P naught is going to represent the initial population, okay? When we talk about initial populations, we're talking about the population when you start measuring it, which means that t equals 0. If you were to plug a 0 in here, you would have a to the 0. Anything to the 0 power is 1. So you just end up with this 1 times P naught. So that's the initial population, okay? Now, the reason why we write it this way is also to help us see where this A comes from. So this R, right? So if A equals 1 plus R is going to give us the percent rate of change. So if your population is growing by 10%, your R is 0.10. If your population is growing by 25%, your R is 0.25, okay? If your population is decaying by 50%, then your R is negative 0.5. So that gives us some interesting properties about A, okay? So if A is greater than 1, Then we have growth. Our population is getting bigger. So that happens when your growth rate is positive, then you're multiplying by something bigger than 1, and your values are getting bigger and bigger over time. If your A is between 0 and 1, that means that your R was negative and you are decaying. Your population is getting smaller over time. So when we look at that base number, we can determine if we have growth or decay based on what that number is. So one key difference here, okay, we've talked about linear functions a little bit with average rates of change and just y equals mx plus b. A linear function we start with because it has a constant rate of change. That's the slope. It's always changing by the same amount. An exponential function has a percentage rate of change, which means that when we go from one point to the next, it always changes by the same percentage, not the same fixed amount, that's linear, the same percentage. So I grow by 50% and then by 50% and then by 50%, right, as we go along. So let's look at some examples of how we apply these exponential functions. These are going to come up in context a lot for us during the class, so we want to make sure we're comfortable with the basics. So here, I want you to consider there's 4 functions down here below, 1, 2, 3, and 4, and they each represent the population in thousands of a different town and how its population changes over time. So each one of these represents the population of a town, and it's in thousands. So if you were to plug a number in like 5, that would mean that we were talking about the year 2015 because it's in years since 2015. And if we were to plug in a 5, if we got a value of say 30, that would be 30,000 because of the units that were given here. Okay, so I want you to look at these 4 town populations and I want you to answer the following 4 questions. So which town has the largest percent growth rate? So if we're trying to figure out R based on this, which one has the biggest R? Part B, which town has the largest initial population? That's our P naught, that's the number out front. Which town has the largest population in 2015? So we have to figure out what the population is for each one of these at time equals 5. And then part D, which towns are growing and which ones are decreasing. So that's where we're looking at our base number and comparing it here. So I want you to take about 3 minutes. Okay, the TAs will walk around and see if you can answer these 4 questions about these 4 populations.
Professor,
Yes.
there's no TAs here except for me, it seems. So do you just want me to walk around and?
Oh, sure. I knew one of them was sick, but I don't know where the other one is.
Oh, never mind. There's one of them. Sorry.
Okay. All right, take about 30 more seconds to finish up whatever part you're working on. All right, so let's take a look at the answer to these questions. For part A, we want to know which town has the largest growth rate. So remember, the growth rate is the R from the base, where the base is 1 plus R. So here, if we look at what the base is, we have 1.37. If the base is bigger than 1, then the R is pretty straightforward because it's just going to be this decimal. So 0.37 or 37% if we report it as a percentage. And similarly, if we jump down to D, this one's greater than 1. So we can just figure out what this decimal is. So 0.28 or 28% growth. Now, if our base is less than 1, remember that your base is 1 plus R. So if we set this equal to 1 plus R, I'm going to do this down here for a second where I have a little space. So if I have 1 plus R equals 1.068, I'm going to be subtracting 1 from both sides. So what's going to happen is I'm going to end up with a negative number. So when I subtract that over, I get negative 0.32. So again, your R can be positive or negative depending on if you're growing or decaying. Similarly here for 0.35, I'm going to need to subtract 1 from that, and I get R equals negative 0.65. So once I have all of my percent growth rates, I can look and think about this on a number line and think about which one is the furthest to the right on the number line, which is going to be the 37%. Notice that I'm taking positive numbers over negative numbers because, again, I'm thinking about it on a number line and where things fall, and I'm looking for the one furthest to the right. So this one's going to be the largest growth rate here. Part B is comparing initial populations. So for initial populations, we're considering all of the values that are starting off our population. So 250, 1200, 125, and 500. So at time equals 0, each of these factors becomes 1, and we're left with the initial population. So the biggest one here is this 1200. Okay. For part C, if we're trying to figure out which town has the largest population in 2015, we are considering what happens at t equals 5, because remember, t is in years since 2010. So if we want to know what's happening in 2015, we need to look at the population at t equals 5 for each of these. So I plugged these in, and you can double check my math on this because I did it kind of quickly, but these are the numbers I'm getting. So 1207 for the first one. For the second one, I'm getting 174. For the third one, I'm getting 0.656. And for the last one, I'm getting 17.99. And I rounded a little bit. One thing that's really important to remember here as we're talking about these is that these have to be presented in thousands. So I would either need to have the word 1,000 after my number, or I could multiply my number by 1,000 and then not include the word. So either way is fine. So here, this is, 1207 thousands, right? It sounds goofy, so it might make more sense to just multiply everything by 1,000. But here we're actually just comparing which one's the largest. So since we're multiplying everything by 1,000, we can just look at these numbers to see which one's the biggest. So here, this 1717 is the biggest of these populations. So population 4 is going to have the largest population in 2015. Finally, I want to know which functions are growing and which ones are decaying. So again, I go back to this up here. If my A is greater than 1, I have growth. And if my A is less than 1, I have decay. So for growing, I have population number 1, because that's greater than 1, and population number 4, because that's also bigger than 1. For my decreasing populations, I'm looking for things that are less than 1 in the base. So that is populations 2 and 3. Okay, so that's sort of how we evaluate these types of functions and the types of things we want to do with them. We also want to be able to look at these graphically and in a few other ways. So we're going to try a couple more examples as related to exponential functions here. Let's see if I can get all 3 on the paper. So we have 3 practice problems I want you to try, and they're all different. And I'm going to label this graph a little bit better so you can see it. But the first question is talking about the amount of adrenaline in the body, and the initial amount is 15 milligrams. We want to find a formula if A is increasing by 4 milligrams per minute, so that's a set amount that it increases the same amount each time, or if it's decreasing by 3% per minute. The objective of this problem is to understand the difference between a percentage change and a fixed change, okay? For example, 4, we're going to be looking at trying to come up with a function looking at a graph. And so the only thing we really need here is our data points. So I'm just going to write these much, much bigger. We have 6, 180. And this is 0, 80. We want to try to use those data points and the fact that this is exponential to come up with something in that form, P equals P naught A to the T. And then finally, we're going to try out a table here where we want to take the data and see if we can come up with a function in the form P equals P naught A to the T. So I'm going to give you 5 minutes to work on these. You probably won't get through all 3 of them. So pick the one you want to try first, try it out, check in with someone next to you. But these are 3 different types of just forming models. And so you may have done this before and this is really comfortable, or you may have never done this before and you're like, this is crazy. But you just have to try, right? So in math, sometimes we just have to try things. It's totally fine if you get everything wrong. We're going to go through it after, but try it out. And again, you're probably not going to be able to do all 3. So you might get through 1 or 2. So decide which one you want to try out and go from there. And then in about 5 minutes, we'll go through the 3 of them. So take about 1 more minute to finish up whatever stuff you're trying out. All right, so let's go through these. Let's take a look at what we get for these different models. So for each one of these, we are trying to set up a model for the situation with the information that we're given. And so for each of these, we should have a result that's something of the form P equals P naught A to the T. Okay, so if we look at example 3, this is going to come up in part B, because part B is where we have our percentage change. And that's what we get when we look at exponential functions. We're changing by a percentage. Here, because we are decreasing, that tells me that R is negative 0.03. And if R is negative 0.03, my A is going to be 0.97. Remember that your base, your A, is 1 plus R. And if R is decreasing, then that R is negative. So now, in my model, I know that my A is 0.97. My variable is T. So when I'm setting up a model, my final answer will have the variable back there. And then the only thing I'm missing here is my initial amount. Remember, we said initial population. It can be an actual physical population of people, but it can also be the amount of something you're measuring. If I go back, it says, suppose the initial amount is 15 milligrams. So that is the number that I'm going to put in front. That's the initial amount. So we have 15 times 0.97 to the T. And as a reminder, we cannot multiply the 15 and the 0.97 to combine them, because the second part is a function. So we leave it just like this, and this is the model for our decrease for this particular problem. Now we compare that to part A that says we're increasing by 0.04 milligrams per minute. So this is a constant change, not a percentage change. So what that tells me is that this part A, is a linear function. Okay, so we're talking y equals mx plus b. So if we're changing by 0.4 milligrams per minute, that's the slope, because that's the rate of change that keeps impacting our function. So we have 0.4 t, and then we know that b is our initial amount in the form y equals mx plus b. So here, our function is linear because the amount at which we are changing is fixed. So this is meant to highlight the difference in the wording when you're dealing with a linear function versus an exponential function. So what you're looking for, so you know which form to put it in. Okay. So that's the first one. The second one, right, when we have a function and we have two data points on there, and we want to set up a model, we need to think about how this data informs our model. So remember, our general form looks like this. So let's start by talking about the initial amount, our P naught, our initial population. We said that that's the population when time equals 0. Okay, so notice that one of the points that I have on my function is the point t equals 0. And I know that when t equals 0, the population is 80. So if you have a point on an exponential graph where you know t or x or whatever the independent variable is equals 0, the other value, the dependent value, that's your initial amount. So I'm going to fill in an 80 here. And so now what I'm missing is the a. So remember, t is your variable and a is a constant. So the way that I get a is by taking the other data point I have and plugging it in accordingly. So what does that mean? That means that my t should be 6 and my population should be 180. So the part I have to be really careful about here in the first step is plugging things in the right order. I know I have to plug in a 6 and a 180, but the 6 is the independent value, so it goes into the independent variable. And the 180 is the dependent value, so it goes into the dependent variable. From here, I would divide both sides by 80. It's going to cancel on the right. And so that's going to give me 2.25 equals a to the 6th. And so now I need to take the 6th root of both sides. There's a couple different ways you can do this. You could use the nth root button, or you can raise both sides to the 1/6 power. Okay, because if you raise 6 to the 1/6, those cancel. So either one of these is going to give you the answer you want. I will show you how I enter this on my calculator just so that you know what it looks like. Let's see. So we have 2.25, and then I'm going to use this caret button right here underneath the clear button, and that gives me a power. Then I'm going to use parentheses. My parentheses are right above the numbers, and I do 1 divided by 6, close parentheses, and hit enter. So anytime you're trying to get rid of a power, you can raise both sides to 1 over that number. So here we would do 1/6. If this had been a to the 4th, we could raise it to the 1/4, so on and so forth. There's also a root button on here if you prefer, but I like to work in fractions. So now I know my a is 1.1447. So I come back over here. Oh, I lost my pen. Okay, there we go. So my a is 1447 after solving, but I still have to put together my final model. So P equals 80, my initial amount, times 1.1447 to the t. So that's what my model looks like for a graph. I can answer all sorts of questions from this. I know that my R is about 14.47%. I could predict the population at other times, like time equals 5. I could just plug in a 5. So being able to get the model from a word problem or a graph is really helpful to be able to answer other questions. So that's how we approach that one. And then our last type, we have a table, right? And so we have a new drug, it's given to a patient. We're trying to find a model for the function, and we have this 5-hour period. Now, you know from the context that I'm asking you to find an exponential function. So there is an assumption being made here that this function is continuous. But we can still work from that. So we have p equals p naught a to the t. That's our form. So again, we want to start with this initial amount. So the initial amount, the initial population, is the value when t equals 0. Well, fortunately for us, we have that data in the table. So we know that when time equals 0, the amount is 250. So we get that right off the table because we know the value when t equals 0. And similarly to the last problem, we now need to solve for a. So the way we solve for a is by picking another point on the table that's not the 0, because we already used that one. So I'm going to use the point 150 to plug in. Now I'm picking this point because I think that t equals 1 makes the algebra easier, but you could pick any point on the table to figure out a. So when I plug in this point, I need to make sure that my 1 goes in for t and that my 150 goes in for p. So I have 150 equals 250 a to the 1. Again, I picked this particular point because a to the 1 is easy because anything to the 1 power is just itself. So I don't need to do roots on either side, right? 5 to the 1 is 5, 10 to the 1 is 10. Anything to the 1 power is just itself. So to solve for a here, all I need to do is divide out that 250. So when I divide both sides by 250, I get a equals 0.6. Now I have my a, but I'm not done because I have to put it all together. So when I put it all together, I have 250, my initial population, times 0.6, that's my a, to the t. So my final model looks like this. And the nice thing about tables is if you want to make sure that it's right, you can just plug in any other point to make sure you get the same value. Okay. Now, a quick thing I want to mention about Wiley Plus. Most of the time, your exponential functions will use the variable t. So when you put in a model, you'll be putting in a t. But if they give you a different variable like x or q, you have to use the variable that's given to you in the problem when you enter your model answer. If you use a different variable, it'll get marked wrong. So just be aware of what the variable is for these types of problems. So that is the end of our exponential quick review. We are going to shift back now to 1.4, which is our economics, and go over that. So hopefully that is a good reminder of exponential functions and what we like to do with them. We will talk about them more as they come up in various ways throughout the course, but that's just sort of a reminder of what exponential functions are and the typical type of calculations that we use. Okay, so the next thing we're going to talk about are applications to economics. And for many of you, this is not a review. For many of you, you've not done this before because this is not something that is taught in a standard curriculum. So if you've done this before, great. But if you haven't, that's totally fine. We're going to be doing some definitions today and talking about different things in relation to economics, because we do a lot of business examples throughout this course. And we want to make sure that we have the same language when we're talking about these types of functions. If you are currently also enrolled in like Econ 103 and 104, you may also be hearing about these same types of things in those courses at some point. So there's sort of three main functions that we talk about when we talk about economics, other than supply and demand. We're going to talk about that later. That's sort of a different concept. But the three main functions that carry through, the first one that we're going to talk about is cost. And so I want to sort of give you a context of cost. When we talk about a cost function, we talk about the cost that it takes to produce an item. So we're not talking about how much it costs to buy it, we call that price, but how much it costs to make something. And so, for example, let's say I got into a business where I was going to be selling UMass sweatshirts at the bookstore, right? My cost to make those sweatshirts is going to be the cost of the material, the cost of the labor to sew them, the cost of the string that goes in the hood, right? So when we talk about cost, we're looking at this from like a producer standpoint. So how much does it cost me to produce something? So when we talk about cost, that's the mindset we need to be in. So when we talk about cost in math, we're going to be using capital C of Q. So our independent variable when we talk about business is Q, because Q represents quantity, right? And so when we're talking about buying things, we're always talking about the quantity that we purchase. Now, as you can imagine, cost is going to be in dollars, right? Where we use the dollars because we're based in the United States. If you were in a different country, you would use whatever the local currency is, but cost has to do with the monetary part of this. So when we start our application to economics, we are going to make the assumption for now that cost is linear, okay? We will explicitly learn how to deal with cost functions that are not linear in chapter 2. But for right now, we're going to take the very basic of cost and say it's a linear function. And so within the linear function, there's two important pieces that make up the cost function. So the first is what's called the variable cost. And we have another name for this I'm going to talk about in a minute. But the variable cost is the cost that depends on how many items you make. Okay, so in the sweatshirt example, that would be things like the materials, right? Because I have to use the materials up every single time I make a sweatshirt. And the variable cost tells me how much per sweatshirt I have to invest. Okay, so per item cost. And this is represented in the cost function as the slope. Okay, so that's your M. The other cost is called your fixed cost. So when you get in the business of manufacturing things, sometimes you have a cost that's a one-time cost. Okay, and so that is considered a fixed cost because you only pay for it once. So an example of a fixed cost in my sweatshirt example would be my sewing machine, right? So I could buy a sewing machine one time, but I don't need to use a different sewing machine for every single sweatshirt. So I only pay for that once, right? If I were to buy a factory to make the sweatshirt, that would be a fixed cost, right? You buy it once. But if I'm renting, then that might fall into variable costs. So fixed cost is a one-time cost. We can find it by looking at what happens when Q equals 0. So if I don't make anything, any sweatshirts or whatever the product is, then the cost that's left is the fixed cost because I haven't even made anything yet. And in the context of y equals mx plus b, this is the b, right? So it's that number you add on at the end. So a typical cost equation is going to look like this. C of Q equals MQ plus B, where M is your variable cost and your B is your fixed cost. Okay? So again, we're making the assumption for now that cost functions are always linear. Okay, we know that's not true, but we will learn how to do nonlinear functions later. So in terms of costs, the biggest things I want you to remember are that the fixed costs you can find by plugging Q equals 0 in, because that zeroes out that term. And that variable cost is the slope of the line. Now, there's another way we talk about variable cost, and sometimes we use the word marginal cost. Okay. And I want to talk about the difference. So variable cost, when we use that term, is based in the assumption that cost is linear. So if you find out you have a variable cost of $12, then the word variable cost tells you that the function is linear. In the linear case, marginal cost means the same thing because it means the rate of change of the function. Marginal is the rate of change, it's on the margins. So for linear functions, these mean the same thing. When we get to nonlinear functions, we will not use the term variable cost. We'll be using the word marginal cost because we can extend that and figure out how to apply this to other types of functions. So what's the takeaway from this? For right now, if you see marginal cost or variable cost, they mean the same thing and they're talking about the slope, okay? So let's consider what this means. We're going to look at two quick scenarios and just think about what our function is going to look like. So we're going to consider this situation where fixed costs are small, but marginal cost is high. So remember, fixed costs are our B, that's small. Okay, small means we're down near 0, so somewhere in this range. But marginal cost is high. So remember, marginal cost is slope. So if marginal cost is high, that means the slope is very steep. Okay, now we don't have numbers to represent this, but we can certainly draw some things that match this, right? That has a low fixed cost, but a high marginal cost. It's steep. I could do something like this, low fixed cost, high marginal cost, right? It's steep, but it crosses through down low, right? I could do something in the middle, something like that. All of those represent this scenario. So even though we don't have numbers, we have a base idea of what this type of linear function would look like. So our B should be down here, it should be low. The B is the vertical intercept. And the marginal cost is high, which means that the slope is steep. Okay, let's look at a different example of the same type of problem. Okay, so here says there are no fixed costs, but marginal cost is small. Okay, so if there's no fixed cost, that tells me that my B equals 0. Right? My plus B, that's just 0. There's no fixed cost. So that means no matter what function I draw, I have to intercept at 0 because there's no fixed cost. But it says my marginal cost is small. Okay, so small means not steep. Right? I'm increasing very slowly as I go. Okay, might look like that. Might look like that. And let me get my red pen. Okay. One thing I want you to notice here, which was the same in the last case, is that all of these are in the upper right quadrant. Okay, because it doesn't make sense for your cost to be negative, because the way we talk about cost is a total amount of cost, and we consider it in the positive realm. So you're not going to have negative $500 in cost, because that means you somehow made money off of it, and that doesn't make sense. So our graphs, they're all above the x-axis, and they're all increasing, right? So you have a fixed cost, and then your variable cost is always adding to that cost. It doesn't make sense for your slope to be negative in a cost scenario. So we always have an increasing function, but how quickly it increases depends on the marginal costs. Okay. So let's look at an example here. Try something out. Suppose a company produces ceramic pineapples. The cost to purchase the pineapple molds and a kiln, which is that giant oven, is $20,000, which are incurred even if no pineapples are made. The cost of labor and raw materials, so the things you're actually using to make it, are variable costs since these quantities depend on how many pineapples are made. The variable costs are $6 per pineapple. Assuming that cost is linear, I want you to find an equation to model this cost function and determine the marginal cost and explain what it means in this context. So I'm going to give you 2 minutes to try to jot down what that function would look like, and then write a sentence about what the marginal cost is telling us. Okay, take about 30 more seconds. All right, so to set up our cost function, we have 2 pieces of information we need. We need the marginal or variable cost and the fixed cost. So here, since my marginal cost is 6, I'll have something like 6Q plus 20,000. Okay, so again, we're setting up a linear function. One of our variables has to do with variable cost, the other one with fixed cost. So that's what a typical equation would look like for this scenario. Now, determine the marginal cost and talk about what it means. We know that the marginal cost here is $6. What that means is that for every additional pineapple that I make, it's going to cost me another $6 towards my total cost. Okay, so that's what that means. So again, for every additional unit that I change in the independent direction, I incur 6 changes in the dependent direction, which here has to do with cost. Okay, so the next concept we need to talk about is revenue. So the revenue function has to do with selling your item. So we're completely removing costs. These are 2 separate things. The revenue is the amount of money that you are going to take in from selling some good. Okay, so revenue, we do R of Q, and the function is just P times Q. Now, this is a little confusing because it looks like we have 2 variables here, but we really don't. So the P here is price, and that's a constant. So that'll either be given to you in the setup or some other way, but the variable here is Q. Okay, so the amount of revenue that you make is price times quantity. So if I were to sell the sweatshirts that I made for, I don't even know how much sweatshirts are these days, $150 each, they're always super overpriced, then my revenue function would be 150 times Q, which means if I sell 1 sweatshirt, my revenue is $150. If I sell 2 sweatshirts, my revenue is $300. It's whatever the price of your item is times Q, where Q is the quantity and it's the variable, so you can plug in lots of different numbers there. Okay, so that's how we think about revenue. So let's assume for a minute that I've decided to open a store that sells gourmet cookies for $9.99 per tin, set up a revenue function for my sales, and determine my revenue if I sell 221 tins of cookies. So for right now, we're going to completely ignore sales tax and we're just going to talk about revenue. So my revenue function here is going to be my price, $9.99 times quantity. So I put my Q in for my model because that's my variable. Okay, so that's what my function looks like just as a model. And now the next question is, well, what if I sell 221 tins? So that means I'm looking for my revenue at 221. So I'm just doing $9.99 times 221. I multiply those together and I get 2207.79. So just like cost, revenue is also in dollars because that's our monetary units here. So when you are doing calculations on revenue or cost, we're going to be going out to 2 decimal places because that's what our currency system allows for, right? That's the change. So unless you're told to round otherwise, you want to do 2 decimal places for things like cost and revenue and things like that. Okay. We are going to skip example 4 because I want to make sure we get to profit. Okay. So we know about cost, how much it costs us to make something. We know about revenue, how much money we take in from selling it. When we put those together, that's when we get profit, right? So profit says that we need to take into account both the revenue and the cost. So this is a little goofy. So revenue, we use R, cost, we use Q. For profit, it would make sense if we used P, except that P is already used in math so often for population that we don't want to confuse it as a population problem. So for the profit function, we use pi. Okay, so pi of Q is profit, and profit is revenue, the amount of money you take in, minus your costs. And so when we talk about this, this is the same Q across functions. So if we talk about the profit to make 100 sweatshirts, it would be my revenue from selling 100 sweatshirts minus the cost of making 100 sweatshirts. So this Q is the same variable across this particular function. Okay. So one of the things that we're really interested in terms of the profit function is what's called the break-even point. So oftentimes when businesses start, before they've sold anything, or if they've only sold a little bit, their profit is negative. And you can imagine that's not good, right? You're running in the red. So if your costs are bigger than your revenue, then you have negative profits. Okay, that is something that happens, and that's okay if you get a negative number for profit. But we really want a business to get to the point where it's making money. Okay, so this critical time, this point where we finally get into the positive realm, is called the break-even point. So the break-even point is when we get to 0, so we're completely balanced. And after that point is where we make money. So if we take our profit function, okay, which is revenue minus cost, and we want to break even, okay, so we set it equal to 0. So we're not making money, but we're not losing money. We notice that if we bring this function over, if we add cost over to the other side, that we have an interesting property about the break-even point. So this happens when revenue equals cost, okay? So if you're asked to find the break-even point, we can set our revenue function equal to our cost function to determine that break-even point. You could also do revenue minus cost equals 0. That's the same calculation, okay? So the break-even point is something that we're going to be doing to find when we start to make a profit. So let's look at one example of this real quick to make sure we understand how this might look or how this might work. So for example 5, it says find a formula for the profit function for the ceramic pineapples manufactured in the previous examples. Graph the profit, marking the break-even point. So here, remember that our cost function, the cost to make these pineapples, was 6Q plus 20,000, and our revenue function was 20Q. We're going to sell them for $20 each. Okay, so our profit function here is revenue minus cost. So we have 20Q, which is our revenue, minus cost, 6Q plus 20,000. Oh, I wrote off the paper, I apologize. So one thing that's critically important here, and the number one mistake that people make when they do profit functions, is that you have to subtract off the entire cost function. So I strongly encourage you to use parentheses because this minus sign has to get distributed to the 6Q and the 20,000. If it doesn't, if you just distribute it to the 6Q, you're going to get the wrong answer. So with profit functions, we are typically going to combine like terms. So we have 20Q and then minus 6Q. That's going to give me 14Q. And then again, the minus has to get distributed. So we get minus 20,000. So my profit function looks like this. So 14Q minus 20,000. This is in the form y equals mx plus b. My b is negative 20,000. So I know that I'm going to start down here. And again, profit can be negative, right? Because you spend more than you've taken in. To find the break-even point, we either need to set this equal to 0 or set our revenue equal to our cost, right? It's going to give us the same thing. Since we've already set this up, let's go ahead and set this equal to 0. So we're going to bring the 20,000 over, divide both sides by 14, and we are going to get 1428.57. So what does that mean in terms of our profit function and our graph? So the break-even point, if we make and sell 1428.57 items, we will then make money after that. Since it doesn't necessarily make sense to make fractions of items, we will often round up to the nearest integer. So in order to be profitable, we need to make 1,429 items because we will have broken through our negative profit here and gotten back into the positive. If we were going to graph that, we are saying y equals 0. We need to find 1428. So these are counting by 5,000s. I don't know if you can see the grid marks, right? So 5, 10, 15, 20. So that's going to be, I'll do another color. So 14's right about there. Okay, because cost and revenue are linear right now, profit will also be linear. So this is the break-even point. 1428.57, comma 0. And then above is where we have positive profits, where we make money. Okay, so this is where we're making profits, and we can figure out our profits at various levels by using this particular function. So if we wanted to know the profit at 3,000, we expect it to be positive, we would just plug in a 3,000. Okay, so that's profit. We don't have enough time to finish out the last example, but I will send you a brief video on supply and demand in case you haven't encountered that before, just so you know how to think about it. Okay, so we will pick up with new functions from old on Thursday.